Good morning, everyone. So we're going to continue with the lecture on mechanism design. Just to recap where we were on Tuesday. So we're going to develop a mechanism that uses an allocation and has transfers as well. And there's no incentive to misreport. So we came up with this mechanism called the Groves mechanism. Groves. Just to show you the elements of the mechanism, I'll just do it on the board, so it goes a little bit slow because it is important. So the first step in the Groves mechanism is finding the optimal allocation. So the allocation that maximizes the sum of social welfare, right? So we have the agents 1 to n, and then we have the value of a certain allocation given the type of agent I, right? And that's the sum, and then we're maximizing over that. Now the payment was then equal to, for an agent I, so the transfer for agent I is then equal to essentially this value here for the optimal allocation. So that we can write it in a different way. So we can write it as max sum I is 1 n bx theta I, okay? But here, the problem is that here it also takes into account the reported value of theta I, if our transfers are simply like this, okay? So that means that the agent I could directly misreport his preferences and get a better transfer, so we want to avoid that. So essentially what we're doing is we're then subtracting theta I. So actually I should, so this is now J here. Okay. So here we have transfer for agent I. So we're summing over all the agents, excluding ourselves. Okay, so this is another way of writing the same as we had before. So before it was like this. The sum of J is 1. So J is not I, right? J is not I of Vj x star theta j. Okay? So these two things. So here we have, so you can do it in two ways. First, calculate the optimal social welfare, and then, given the optimal social welfare, compute the value of everyone else, or you can write it in one go, in one equation, like that. Okay, so these are essentially equivalent. Is that clear? So the difference between argmax and max should be clear, right? So argmax returns the argument. So here we're maximizing over all possible kind of possible allocations here as well. Okay. But the difference here, argmax returns this x here, and max returns actually this sum here. So just to make it clear, this is how it should be. Okay. So this is one thing. And then what we said is, okay, the problem here is that this is all good and well, but this would always result in positive transfers, meaning the agent would always receive a payment as well as their allocation. Okay, so what we said is we then subtract some sort of constant h, okay, which can depend on, so it doesn't have to be a constant, so it can be actually a function of everyone else's types, right? So which we denoted by minus I. Okay, so that's essentially all the types of except agent I. So it's clear that this is a constant from agent I's perspective, because unless he colludes with the other agents, he cannot influence whatever this function is, right? So it's completely, it's a constant from agent I's perspective, right? Is that more or less clear? Okay, so now the big question is, so this is a Groves mechanism. So these are, or sometimes called the Vickrey-Clark-Groves mechanisms, so the class of Vickrey-Clark-Groves mechanisms. And depending on how we specify this, we can get budget balance, individual rationality, and or both. Okay. So remember, if this is really big, like 1 million, right, then we violate individual rationality if we make it really large. If it's 0, we violate budget balance. Okay. So the question is, what should this value be? Okay. And that's the key. So then we get to what's called the Clark tax. Okay, so another economist called Clark came up with a value for, like a function for this. And the intuition is really quite simple, so, but quite nice. So what could this HI be? Well, so we have available all the types except agent I's type. So let's suppose that we have a market that consists only of these other agents. So we're going to ignore agent I for the moment. And we're going to say, okay, suppose we only have these other agents. And we're going to run this market just with these other agents. What's going to be our social welfare? Okay. So we can do the same again as before. So we take the maximum of the social welfare, but excluding agent I. Okay. So what we get is here, is this max J, not I, of V of X, theta J. Okay. So this is the same as saying, okay, let's take out the agents. Okay. So we're going to find an X star, but maybe it's kind of indexed for I. Okay, so excluding agent I. So maybe minus I could be one way to say. Okay, and we say it's argmax. So we look again over all possible allocations. Okay. But then we are maximizing the social welfare, but without agent I in it. Okay, so J not I, V X. Okay, so notice that here we have X. Okay, so we are computing a different allocation, obviously, right? So here we were able to allocate units to agent I. Here, the agent I is no longer present, so we get a different allocation. We get a new allocation. Right? If we remove agent I from the market and we rerun the market without agent I, we might get a different allocation. Because if in the optimal allocation we allocated some units to agent I, now we take out agent I and we say, okay, suppose agent I is not here. Let's take this agent I out of the market. So then we can still allocate it to all the other agents in the market. Okay. Okay, so clearly, so even though these things look very similar, okay, these things are not the same. So this part here, this part, okay, is the allocation where agent I is present and taking out his value, right, his utility. Here, we are maximizing by excluding agent I in the first place. Okay, so it's a very subtle difference, but very important difference. Okay. So these two things, so this thing, so let's call this A, right? And let's call this B, okay? And these two things are different, right? These are not the same. Should be very important. Okay? So the other thing that we can say, what do you think is bigger, A or B, in terms of value? A is bigger? Why?
Because it's with agent I.
Well, so if we is A is like this minus agent I's utility. Right? So we are excluding agent I's utility from A. Okay. It's quite a tricky one, in fact.
Wouldn't it be B, but it would sort of depend on the problem to an extent?
To some extent, yeah. To some extent. But normally, under normal circumstances, especially in an independent private value model, B is always going to be bigger than A. Okay? And that's why is that? Because here we've optimized based on agent I being present, and then we take agent I out. Okay? So now this allocation is actually no longer optimal in some sense. Here we've already taken out agent I, and then we're optimizing. So the allocation that we're getting then is actually better in terms of total utility, right? So we can see that this is always normal circumstances under the kind of models that we are going to consider anyway. B is going to be bigger than A. What does that mean? Right? That means that this whole thing, because this is going to be bigger than this bit, right? So the transfers are going to be negative all the time, okay? And therefore we have budget balance. Okay? Now, do we have individual rationality? Okay. So what is utility? What is individual rationality? Well, if we, instead of the transfers, we look at utility, okay? So let's look at the utility for agent I. Utility of agent I is the transfers, which is this whole bit, plus its own value. So this x is the same x as here. It's a little bit, it's not quite x star, let's do x. Okay. So yeah, but actually this is x star. Well, the notation is a little bit. Okay. So the key here. So this is agent I's value is the transfers plus his utility. Okay. Now we can cancel out. Okay. So now what we're left with is the social welfare of the optimal allocation with agent I minus the social welfare of the optimal allocation without agent I. Okay. Normally, actually we are going to look at a situation where this is not always the case, but anyway, normally the social welfare with, if you remove an agent, you reduce the total social welfare in the system, normally, okay? And therefore, it's going to be individual rational, always. So actually that does hold together. Okay, so therefore, this is always larger than that, so this bit here is always larger than that, so therefore we also have individual rationality as well. Okay. So this is a nice one. So we have a function h, which is kind of in between the social welfare, I guess, with agent I and without agent I, or excluding the agent I. So we get budget balance and we get individual rationality with this H. And this is called the Groves mechanism with Clark tax, or with actually I think it's called Clark pivot rule. And sometimes, and often actually, this is called the Vickrey-Clark Groves mechanism. Okay. The VCG mechanism, VCG. Okay. This is kind of the basic mechanism in mechanism design. And why is it called Vickrey? Well, we get to that. Let's now look at examples, right? So this mechanism is all good and well in theory. What you need to do is start practicing with it to understand how it works. Okay. So that's going to be really important. So let's look at the simple setting, the simplest setting we can imagine. That we want to allocate a single item. Okay. So we looked at last time at the combinatorial problem, but let's forget that for the moment. We'll get back to the combinatorial problem, and then you can calculate the transfers for that, and then we'll give you a bit of time to do that. But let's together first do the very simple setting with one item. Okay. So we have one item, and it has to be allocated to one of the agents. Okay. So let's do it a little bit abstract. Okay. So So let's use the notation here, so you can map that to the notation that maybe we had last semester. Okay, so we have one item, and so where the value, so maybe we have a certain value for having that item. So Vx of theta I is, say, theta I if I is allocated the item, if agent I is allocated, and is 0 otherwise. Okay. So this is very simple, right? So my value for a certain allocation is theta I if the item is allocated, and if I don't get the item, obviously it's 0, right? So all allocations where I am getting allocated an item, I'm going to be happy. Okay. Now the possible allocations that we have is simply we can either allocate it to agent 1, we can allocate it to agent 2, etc. And then maybe n is the number of agents. Okay? So this is the possible allocations, right? So if x is I. Okay, so that's how we could write it down. So here we have possible allocations, there's only n agents, so we have n plus 1, right? So actually we have also 0. So we can also allocate it to no one. Okay, so good. Okay. So now let's keep it a little bit abstract in this case. Intuitively, you can tell that maybe the top agent, we don't care really about all the agents. So let's see. Let's look at the optimal allocation first. Okay. So what is the optimal allocation? Well, it's allocating the item obviously to the person with the highest theta I. Right? So let's call that theta first. Okay? Okay? So this can be any value. Let's keep it a little bit abstract. So theta first, suppose that's the one with highest value. Okay? What's going to be the transfer of agent I? Okay, so let's say T first. So let me just use a different notation. Okay. Suppose that so first. Okay. So suppose there's an agent called first. That's the guy with the highest value. So and we want to compute the transfers of these agents. Okay. So how do we do that? Well, we have the first part, which is the maximum social welfare, excluding the value of agent I. So that's this, yeah? Okay. Minus this function h, I. Okay. Theta minus first. Okay, so everything except agent I. Okay. So what do we get? Hi, what's hi? Second highest bid. Yeah? So if we exclude agent I, so h first, sorry. If we exclude agent first, and we do the maximum allocation, obviously it's going to be allocated to theta second. Okay? The second highest bidder. So what we get is equal to 0 minus theta second. Okay? So we're back at the beginning. So this should look familiar. This is the victory option, second prize option. Okay. So we've done a whole tour around and we get to the same point. Right? We had, in last semester, we said victory option is incentive compatible, strategy proof. I showed you a proof for that. Now I build up this VCG mechanism from the ground up, looking first at the groves part, then having this constant h, then seeing how we can have a clever h, and now we're back at the second price. But obviously, this one is much more powerful because we can look at combinatorial problems, right? Not just the simple options, the options that we had before. So hopefully, does that all make sense so far? Q not, Q no. Okay, so now I'll go back to the slides. So this is all on the slides, so don't worry about, you don't have to take too many notes. But let's look at the combinatorial problem we had last time and apply the VCG mechanism to that problem. Okay, and so I'll leave you to do that. I'll give you a few minutes. Let me just. That's all. Yeah. So even the single item setting. So, okay. Right. So this is the problem we started off on Tuesday. Same problem. Okay. We already know what the optimal allocation is. We also know what the optimal allocation is without agent 1 and without agent 2. But the key now is to find the transfers. And for ease of reference, I've put the equation on there. It's slightly different terms. So here F here gives us the optimal allocation with all the agents in it. Okay? And so we are summing here the values all the agents except agent I of the optimal allocation with agent I. And then we are making a new allocation here. Okay? So a new allocation without agent I. Okay, so I'll give you a few minutes, and what you need to figure out is the payment of agent 1 and the payment of agent 2, the transfers. And whilst we're at it, maybe you can calculate the utility as well. Okay, so this could be an exam question. Example of an exam or assignment question. So let's see how we're doing, and then you get an understanding of your grasp at the moment. So if you have any questions, let me know, but I'll leave you otherwise to it. And well, you can work together. transfer have to be both negative, so okay, so you can't end up with positive values. That's a mistake.
So don't worry so much about the equations. So think about the concept of having the social welfare without agent I, and then having a new recomputing the bracket without agent I. So you know, rather than staring at the equations too long,
Yeah, you don't, the equation can distract you from the story, which is not so complicated. It's not too difficult, but the equations make it look a bit. But then, unfortunately, that's not really a better way to write. So, do you need a bit more time, or you? What do you think? Okay, so shall we see what you come up with? So let's do it bit by bit, right? So let's take agent 1. And then let's look at this part first. Okay, for agent 1. So how much is that? 90? Yeah. Yeah. And why? Because the efficient allocation was 190, right? And then we take out agent I's contribution to that, and we end up with that. Right? We had that before. So this is the gross bit, remains unchanged. Okay. And now we have the H part, this part here. Okay, this is the HI. How much is that? 150. 150? Everyone agrees? Yeah? How did you get to that?
Ignore agent 1, see the maximum utility value to.
Yeah. Okay. So you take out agent 1 from the market, you pretend he's not there, you recompute the social welfare. In this case, we only have one other agent, so it's easy. And we can easily see that under the 50 is the value that maximizes the market without agent I present. 60. Yeah, and that's then minus 60. Okay, so that should be answer for T1. What about T2? Yeah.
100 minus 180.
100 minus 180, yeah. 180. Okay. So, and what about the utilities? Agent 1?
40?
40. So it's 100, yeah, minus 60, 40. And agent 2?
90 minus 80.
Minus 90 minus 80 is 10. Yeah. Okay. That's, yeah, so this is what you should have come up with. If not, just try it again at home to make sure that you understand it properly. Okay. So this is the most basic version. And in the exam, I'll ask you for more difficult one. Okay. So you have to understand the basic. Okay. So let's look at a more difficult one. Okay. Where we will see that in fact budget balance does not always have to hold. Okay. So actually we'll look at an example where budget balance does not hold. Okay. So this could be a question in the exam, although you know probably going to change. Actually, there was a question like this in last year's exam. It was actually, yes, very similar to this. Okay. So there are two agents, buyer B and seller S. There are three possible allocations. It goes to buyer B or it goes to seller S. Okay. The seller currently owns the item and it could sell it on the general market for 4. Okay, so the seller has, so that's important. So what does value mean, right? So what does the value or utility mean for an agent, right? So it's a willingness, if you're a buyer, it's a willingness to pay. But we can now look at it from a seller's perspective as well. Okay, so what does value of 4 mean for the seller? It means that if he gets 4 for the item, he breaks even. If he gets more for the item, he's going to make a profit. Okay? So it doesn't matter. So we've looked at, all the problems we've looked at so far, everyone's a buyer. Okay? But we can also look at systems where we have buyers and sellers. But the sellers is kind of reverse, right? They want to have, they're getting rid of an item, right? So they already have the item and they're getting rid of it. So the seller could sell it on a different kind of market for 4, so he needs to get at least 4 to break even. Okay? So if the buyer gets the item, the seller effectively makes a loss of 4 if he doesn't get any money in return for this. Okay? So getting rid of the item gives him a value of -4. Okay? So the buyer has a willingness to pay of 6. For the item. So what does that mean? So this is very different from what we've looked at so far, but the thing what I want to show you is that you can apply this mechanism in settings you've not encountered before. And that's what if you truly understand the mechanism, you can do that. Okay. And to test your understanding in the exam, that's what we'll try to do, rather than your ability to memorize, we try to find some interesting settings that you haven't quite encountered. So the value, so I'm giving all the specifications here. So if the buyer gets the item, so we're not looking at transfers yet, right? So just basic value. So the value for the buyer for getting the item is 6, so his utility will be 6, if we ignore the transfer. So the utility for the buyer, if the seller gets the item, is 0. And the utility of the buyer, if the item gets thrown away, is also 0. Okay. Now, we have the same for the seller. If the buyer gets the item, he's making a loss of 4 because he could have gotten 4 on a different market. So he's giving the item now to the buyer. So if the buyer gets the item, he's got utility, the seller has utility of -4. if the seller keeps the item, he's going to sell it. He's going to break even. So it's going to be sell it on a different market. So his utility for is 0. And then if it gets thrown away, then it's again -4. Okay. And so this is a slightly different setting. And again, so what's going to be the transfers in this case? Okay. So maybe we should do that one together. Because this is a little bit tricky, because what do we do if one of the agents is not in the market? Okay. So let's have a look. So the transfers for, so obviously, first of all, what's the optimal allocation in this case? Yes.
That B gets the item.
B gets the item. And what's the social welfare there? 2. Yeah? Okay. So there's a surplus of 2 to be made by exchanging the item from the seller to the buyer. Okay? So that's where trade happens, and the surplus is generated in the market by this exchange of transferring from the buyer to the seller, from the seller to the buyer. Obviously, the seller is not going to, let the item go empty-handed. So that's why we have the transfers. So let's compute these transfers. Transfers for the buyer. Okay. So what's the first part? So we have the 6. Okay. So 6 is so if we exclude, say, the buyer's utility, right? -4. Yeah. Okay. So it's essentially it's 2 minus 6, right? So it's -4. So yes. -4. Okay. And now for the H part, for the Clark tax, or Clark-Pivot rule. So now we're going to take out the buyer from the market. What's going to be our utility? Okay. 0, yeah? So there's no buyer anymore. So we can't allocate the item to the buyer anymore. So no trade is taking place, so it's 0. Okay. Okay. Now let's look at the transfer for the seller. Okay. Anyone else? So what's the first part? Okay. So this time, so we have the value. So the allocation is social, one that maximizes social welfare, but we exclude the value of the seller in this case. So we get. Yeah. 6. That's right. Now we do get 6. Okay. And then minus, well, there's no seller, so there's no trade. So 0. Yeah. Okay. Because we're taking out the seller from the market. We can't trade the item anymore. There's no item. Okay. So therefore it's 0. Okay. So now. That's interesting, okay? So this value, transfer, is negative. So let's look at the utilities, okay? So utility of the buyer, so he's got 6 minus 4 is 2, right? That's his utility. Right? So he's getting 6, the value, okay? And then he pays 4, so his utility is. What about the seller? His utility?
-4 plus 6.
Yeah. So what's curious, so we can see that it is individually rational. Okay? They both have the utility of 2. But there's something strange going on here. What's interesting here? Yeah.
So I can sell it on the market for 4 when it needs to be 4.
No, so if he sells it on the market before, he gets utility of 0. That's the situation where he breaks even. Okay.
We've magicked 2 value from nowhere.
Yay! That's right. Okay. The surplus from trade was 2, but here we have utility of 4. And we can see if we add these 2 together, the transfers, right? There's a positive of 6. So we're giving 6 to the seller, right? And we're getting 4 from the buyer. Okay? So the mechanism has a deficit of 2. He has to get this from somewhere else. So the key thing is that we thought VCG is budget balanced, and in many cases it is, but not in situations, for example, such as bilateral trade. Okay? And there's, in fact, there's a theorem. I'm not sure if I have it here. No, I haven't. I don't have it. That you cannot always, in all circumstances, get efficiency, budget balance, and individual rationality. You can't satisfy it always together. There's always counterexamples where one of these cannot hold. Okay? So in this case, budget balance is a problem. Obviously, we can fix it by not allocating anything to anyone, right? But that means we don't have efficiency. Okay? And we could find different H value so that budget balance is satisfied, but then we're going to break individual rationality. Okay? So there's always situations where we cannot find a mechanism, a single mechanism, that always satisfies with budget balance, individual rationality, and efficiency. Okay? So such a mechanism does not exist. And this is already a counterexample that even the VCG mechanism is not always budget balanced. And why is that? Well, that's because there's agents with essentially negative utility in the market. So there is a theorem here. So okay. So you don't have to remember this for the exam. I'm not going to ask you about it, but it's just to give you an idea. So the growth mechanism with Clark pivot rule, so the VCG mechanism, is strategy proof and efficient, and also it's individually rational if no agent ever has a negative value for an outcome that will be selected if that agent were not present. I'm not going to go into details there, but and it's weak budget balance if whenever an agent leaves, this never makes the combined welfare of the other agents, not considering payments, should be greater, smaller. Okay. Okay, the combined welfare of the other agents smaller. Okay, yes. Okay, so you can't have the situation there an agent leaves the market and that reduces the welfare that other agents receive. And in this case it is, because an agent leaves the market. If the agent leaves the market, the social welfare of everyone else is going to be 0, whereas if the agent is present in the market, the social welfare of everyone else was 6. Okay? So social welfare is reduced by taking out, of the other agents is reduced by taking out an agent. Normally this should increase because in the item, in the combinatorial auction, if you take an agent out, the other agents should benefit from that because they're going to get that item, right? In this case, you take the agent out and actually the welfare of the others actually decreases. Okay, that's because of in the exchange situation. But as I said, so don't worry too much about this. It's just to indicate that it's not always individually rational and not always budget balanced. That's the key to the welfare here, and not exactly the conditions under which it happens. Okay. Right. So, any questions so far? So now, so I've done the examples from the slides. What I'll do as well, because I'm probably not going to be here in the revision week, so probably I'll do the one that was from last year's exam. You can do that one another time. Okay, so we'll do more exercise together. You'll also get the opportunity to do the exercise in the assignment as well, so that hopefully will prepare you as good as possible for the exam. But make sure that that you understand at least the stuff that's on the slides so far. Okay. So there's many other issues that now we've ignored. Okay. And I'll go through a couple of these. So this is the basis of mechanism design, and there's lots more to be said about mechanism design. But we're not going to go into more details. Instead, we're going to next week look more at applications. But one of the key assumptions here is that the growth mechanism requires exact optimization. Okay? So what do I mean by that? So when we looked at the combinatorial problem, in order to, because essentially the utility functions are aligned with social welfare, we were maximizing social welfare, right? So, and the utility function of the agent was equal to the social welfare minus this constant h, right? So if we're not maximizing the social welfare, then, well, if we don't optimize, or if we take a suboptimal solution, then the agents might be able to strategize to get a better solution, essentially, if they knew the whole system. So the key thing is that the growth mechanism, all the growth mechanisms, require exact optimization. You have to solve these problems optimally. And we saw the combinatorial problems become computationally complex, so they're called NP-hard problems. Yeah. So the VCG mechanism is an NP-hard problem. And we will have to compute the social welfare not just once, right? But we have to then take agent 1 out, compute the social welfare again optimally. Take agent 2 out, compute again. But if we have 100 agents, we have to compute the optimal social welfare 100 times. Okay. So this can become really quite computationally intense. And so there's kind of solutions that we can get around that. So we can still, there's this concept called maximum in range, where we can have approximate solutions and still VCG is still valid. So what we're doing there is that we say, okay, let's limit instead of having x, instead of having all the possible solutions, all possible allocations, let's take a subset of that, x prime, say, which is a subset of x. Okay. This subset does not depend on any of the reports. We specify in advance what this subset is. And then, instead of maximizing over x, we're going to maximize over x prime. Okay. So this can be any smaller set of x. Okay. As long as it does not depend on the report, we can still maximize over x prime, and then we maintain incentive compatibility. Because the agent cannot misreport. They cannot, by misreporting, they can't get to a solution that's not in x prime anyway, right? Even if that's more efficient, because we're only maximizing over x prime. Okay? So that's why it's very important that x prime does not depend on the reports. So we can choose any subset of x and maximize over that. And what's the advantage? Well, we can choose this subset so that it's much smaller, and we can essentially get around the complexity problem. But we then we have no longer have efficiency, obviously, because we might be excluding the efficient solution. Okay. So an example is so here, so reducing x. For example, we say that okay, in all the allocations that we suppose we have a really big combinatorial problem with maybe 10 different items in the set. We say okay, we're going to allocate at most 2 items to each agent. So we can reduce all the possible allocations by restricting. So okay, we're going to say we allocate only 2 items to any agent. So we're not going to consider even allocations where we allocate 3 items to an agent or 4. So we reduce the set possible allocations. And in doing that, we could move the problem from being NP-hard to a polynomial type of solution. But we lose efficiency in that case. But we don't, key thing is, if we do it properly, we don't lose incentive compatibility. But we can't just do it naively. So we can't use a heuristic search algorithm, for example, hill climbing or whatever. That breaks incentive compatibility. Okay. So I think we don't have much time. So there's a few other things maybe I'll do that. No, actually, I'll skip this bit about preferences. One more thing is about the optimal option. So far we've maximized social welfare, right? But an auctioneer may want to maximize something else. So they might be interested in maximizing revenue. And the problem with VCG is that sometimes the revenue for the auctioneer can be zero. Right? If we take, it could be that it's not collecting any transfer. For example, in situations where not enough competition, essentially, in that case the revenue is going to be zero from the auction. Yeah. So if, say, like in the victory auction, if the second highest price is zero, right, then we're going to make a zero profit. Right? So how can we counter this? Well, in simple settings, these are called single value domains, you can just simply set a reserve price, for example. So I'm going to set a minimum price. I'm not going to sell below a certain minimum price. So it's kind of I'm putting out a fictitious agent in the market, which has a value equal to the reserve price. And then the payment is the maximum between the reserve price and the transfers. So you can always guarantee yourself reserve price. But the problem there is that if the reserve price is set too high, and if the value of the highest bidder is below the reserve price, you're not going to allocate the item to anyone. Right? So there's a chance that the auctioneer keeps the item, but it doesn't want the item. Right? So if you set the reserve price too high, then you might not sell the item. But if you do sell the item, you're guaranteed to get at least the value equal to the reserve price. So the allocation is no longer optimal, it's no longer efficient in some cases. So that's why the revenue equivalence theorem doesn't hold, because the revenue equivalence theorem, remember we could say option A and option B result in the same revenue for the auctioneer, but that's only if the allocations are the same. And it's just the payment that we change. But in this case, we also change the allocation because we don't allocate agents below the reserve price. Okay. So that's just a very quick kind of introduction into things that, we can look at not just social welfare maximization, but also maximizing the revenue for the auctioneer. Okay? So next week, we're going to look at sponsor search and indeed.